Okay, now let's actually jump into how we derive these boundary layer equations. So we're going to start off. Yeah, we're going to start off with momentum. And specifically, we're going to be focusing on x momentum. Now, I am using the non-dimensional form of these. You're like, what's that? We didn't go over it. It's in a different chapter. I could have done it, but I don't know. Maybe next time. Maybe next time, okay? Either way, this is a non-dimensional form. So when all these primes are, that's what it's coming from. It's all the primes. So I'm going to have rho prime, u prime. This is going to drive me insane to write this out. There is a reason we don't use the full Navier Stokes at the time. You're like, so far this looks pretty similar. It does, until I get to here, and you're like, what? But we're non-dimensionalizing things, and so I have to actually make sure that our pressure and everything else is also non-dimensionalized, and so I do that by bringing in my Mach number. Okay, I am so grateful that I have a whiteboard I can just move around, because I was constantly running out of space when I was doing this on an actual whiteboard. I think I'm going to manage to fit it. Can he do it? The answer? Maybe. Maybe. Okay. So cool. We have this massive equation. This is the full equation. I don't want to deal with this full equation all the time. I can, like that's if you want the most accurate results, that's what you do if you really want it, but you get really, really, really accurate results even without it. So let's go ahead and draw a picture here. So this is some distance c for my infinitely thin flat plate. And this right here is delta. That's not delta, that's the thickness of the plate. This distance right here, that is delta. And delta, just so you know, is much, much less than the chord, much, much less than c. I need that value because that's going to really help me out as I keep on moving forward. Okay. So now we need to start doing that whole order of magnitude thing. So I have to look at each of these terms all the way through it and say which one of you actually matters. Okay, well, how do we do that? Well, one at a time, okay? I'm just being honest here, we do it one at a time. So to do this, we can first look at our continuity equation. So looking at continuity, you're like, why am I bringing a second equation? We need it. I'm sorry, we need it. Rho prime u prime dx prime plus del of rho prime v prime dy prime. That's equal to 0. Okay, now while that might not mean much to you, what we're going to quickly realize is that dx, well, that's on the, it's a much bigger one, okay? Like if I'm saying that c is the full length, like c is equal to 1, well then dx is, proportional to 1. So all the rows, this guy right here, this guy right here, and dx, they're going to be order of 1 because they're like the full amount. They're what I'm comparing everything else to. Okay, so that means that this guy right here, also order of 1. My velocity in the v direction, also order of 1. dy prime though, remember that we're going in, that's the delta direction. And delta is way, way less than c. And so dy prime is on the order of delta. Okay, so it's going to be smaller than the rest. It's not taking the full length. Okay, so let's see. Oh, I apologize. V prime is the one I didn't know. My bad, my bad. Okay, there we go. V prime, but it's not on the order of 1. I was thinking like this doesn't tell me anything. Okay. So then if I want to solve for this, I'm going to kind of solve for v prime. I'm going to move everything around. Actually, I'll just go ahead and replace everything I know is on the order of 1 first. So I have order of 1, order of 1 over order of 1 is equal to order of 1 v prime order of delta. That equals 0. And then I can solve for v prime, and I find out v prime, well, you have to be on the order of delta. So what does that mean? It means that v prime doesn't change much. It changes a very, very small amount for everything else. Okay, it's going to be a small, small value. Okay, so great. How does that help me? Well, it helps me quite a lot. So I'm going to go back up to this top equation and we're going to start looking at all of them and see which ones fall out once you get this one written down. So we'll go back up and I can now use what I've learned to tell myself out. I'm going to go ahead and kind of erase these lines right here because they're going to get in the way. So this one right here, just writing it out but underneath it, this is order of 1 times order of 1 times fraction of order of 1 over order of 1. Okay, nothing there, that's just all order of 1. That's fine, okay? Second one right here, I have order of 1. I'm going to need to just erase this because it's taking my space. There you go. Order of 1 times order of delta, okay, times order of 1 over order of delta. Okay, so the order of deltas cancel. It's still just order of 1. Okay, so this guy right here, order of 1. This term right here, order of 1. And I keep on going through it. We're going to skip this guy right here. We're going to skip talking about this one right here for the moment. And we're going to go and look at this term right here. Okay. So first off, d dy, that's like 1 over order of delta here. And so if I multiply that through, I'm going to have dv dx, that's order of delta over order of 1. And I'm going to have du dy, that's order of 1 over order of delta. And if I multiply all that through, what do I get? I get 1 over Reynolds number infinity times, let's see, order of 1 plus 1 over order of delta squared. And remember, if you divide something by a very small number, you get a huge number. So one of these things is going to be much more important than the rest. Okay. Now, we're getting closer here. No, I didn't mention that this one right here, this was also order of 1, my bad. Order of 1. For this guy right here. So I rewrite everything now. Using what I know, I get a very simple equation. I get order of 1 plus order of 1. You're like, why is it all this order stuff? We're almost done with it. Is equal to negative 1 over gamma m infinity squared times order of 1. Okay, plus this whole 1 over the relative number infinity times order of 1 plus order of 1 over delta squared. Okay, now my Reynolds number is going to be big. Okay, it's going to be very, very big. And we're going to make an assumption here, okay? We're going to say that it's big, and it's actually big enough that we can say that it's on the order of 1 over delta squared. Or I could say that 1 over the Reynolds number infinity is on the order of delta squared. Okay, so using that, I multiply everything through, and I start to simplify it some more. So I get order of 1 plus order of 1. I really hate having to write this out, but I'm stuck doing it. And so I have then order of delta squared, which is tiny, because it's 1 over my Reynolds number, times order of 1 plus order of 1 over delta squared. And what we're going to see is that this term right here is tiny then, okay? Because it's being multiplied by order of delta squared. And so what does that mean? That means that this term right here can be neglected. Because it is very, very, very small changes. And so I don't have to include that one term. All that work to get rid of one term. I'm sorry, okay? I know that was painful. You're like, why in the world did we do that to ourselves? It was all so we can figure out that that one term is tiny and we can get rid of it. And so then going back to our regular, not non-dimensionalized Navier Stokes equation, we get for x momentum the following. There we go. Okay. So now we're going to do a similar thing. We're going to do it for a y momentum. Because we got to this one, we learned we can neglect one term, but we got to neglect one term. There's at least one. Come on. That was a triumph, people. That was a triumph. Okay. So let's write out the y momentum now, and we'll see. Once again, this could be non-dimensionalized to start. And we'll see what we can neglect here. So rho prime u prime, dv prime dx prime, plus rho prime v prime, dv prime dy prime, is equal to, once again, negative 1 over gamma infinity squared, dp dy, plus 1 over a Reynolds number, d dx prime, now this is going to go a lot faster than last time because we already know how all these things move around. So we really don't have to worry about it too much. Okay, so first off, rho, u, dx, all of those guys, they are on the order of 1. dv and dy, those in the order of delta. This guy's on the order of delta squared. And so using that, I can go through this and write this pretty quickly and see what's going on. So I have order of 1, that's the density. Order of 1, that's the velocity in the x direction. dv, that's order of delta over order of 1, because dx is also an order of 1. I keep on going across, and you're going to see that this time, the order of deltas aren't canceling, and I'm going to actually have a lot more terms, which are small. I should have written that properly. My bad, my bad. There we go. Almost there. Order of delta over order of 1 plus order of 1 over order of delta. Okay, so I go through all of that, and what I find is that that is tiny. It's on the order of delta. That is tiny. It's also in the order of delta. And this whole term over here is also tiny. It's on the order of delta. And so the only thing that's left in the end is dp dy, which is huge by comparison. And so it's simply equal to 0. So all that work this time did a whole bunch of effort for us. Like it actually got rid of a bunch. Like this is way simpler. And we're simply saying that our pressure gradient doesn't change in the y direction. So whatever pressure I have on the surface in the y direction, that is what I'm feeling throughout the entirety of my boundary layer. Okay. How about the energy equation? I'm not going to do it for you. I'm sorry. That one takes way too long. But it works, okay? Just you take more or less the same stuff and you can figure out what it's going to do. By the way, the x momentum and the y momentum especially is where we wanted to show how this simplifies amazingly when you go through this. Okay, so we'll stop there.